We're picking up with our lessons in Chapter 1 of Organic Chemistry, looking at Section 3, Electrons, Bonds, and Lewis dot structures. I imagine that this section will be quite a bit of review and should come easily for us. We're defining the term of a covalent bond. Really is just a shared pair of electrons between two atoms. So for instance, if we have hydrogen with its one valence electron forming a covalent bond with a second hydrogen, we have a molecule form when we have literally an overlap of those two shared electrons. And that's truly the definition of a covalent bond, is an overlapping of electron orbitals to form a shared pair. And in this diagram, what we're looking at is an energy diagram representing energy as a function of the internuclear distance between those two hydrogen atoms. And so we have an optimal distance to help reduce the repulsion of two nuclei. So just think of this hydrogen atom with its positive proton inside the nucleus, and a second hydrogen atom with its positive proton with its nucleus there. And as we begin to bring those closer and closer together, you see the optimum distance being of the lowest energy possible. And so from completely separated to an optimal distance, but keep in mind if they're too close, there's a repulsive charge, like charges repel. And so if these two positives are absolutely too close, that's not ideal either. So that optimal distance here between two hydrogen atoms, approximately 0.74 angstroms between those two nuclei. But, walking away from this picture, we're just saying there is an optimal distance for a single bond in which electrons overlap orbitals to form a shared pair of electrons. And we understand really that we can predict what type of bonds are going to form based on electronegativity. When we think about drawing Lewis structures of an atom, we realize that the number of valence electrons can easily be found just by finding the location of the element on the periodic table. So the valence electrons, remember, they're the ones that are most interesting to a chemist. They're the ones that are available for bonding in the outermost shell. Protons, we know, are positively charged. Electrons are negatively charged. And neutral atoms have the same number of protons as electrons. And so group 1A, the hydrogen, lithium, sodium, potassium, rubidium, cesium, all of these have one valence electron. Group 2A, such as beryllium, magnesium, calcium, strontium, all of these have two valence electrons. That's why they live where they live on the periodic table, and so forth. Group 3A has 3 valence electrons, 4 valence electrons for carbon's family, 5 valence electrons for nitrogen's family. Oxygen's family has 6, the halogens have 7, and of course neon on down have 8 valence electron, where helium has just 2 valence electrons. So the drawing of the Lewis dot structure really is just using the elemental symbol just a generic letter X, and then we use dots around the symbol to represent the valence electrons. The order would have us place 1 around each side first, and then go back and assign partners until we reach the maximum level of 8. So any element represents its valence electrons with dots around its elemental symbol, known as a Lewis dot structure of the atom. And those Lewis dot structures come from the valence electrons. Let's find, just as an example, on our periodic table, we have the element lithium with an atomic mass, we'll say close to 7, and its element number 3. Of course, its atomic number is telling us the total number of electrons. And so it has 3 protons and 3 electrons in it. We would know that it has 7 minus 3 is 4 neutrons as well. But when we write out its electron configuration, 1s2, 2s2, 2p1. Whoops, I just wrote, we wanted 3. There, I repaired that. Thank you. 1s2, 2s1 represents the 3 valence electrons. There. 1s2, 2s1 are the 3 electrons that belong to lithium. However, it has just 1 valence electron. We know that it would be represented with just a dot around its symbol. Here's beryllium, Be, atomic number 4. Therefore, when we look at its valence electrons, there are 2 to represent, and we see that we place 2 dots around its symbol. Boron in group 3 with 3 dots. Carbon in group 4 would have 4 dots. Nitrogen has 5, so we see 5 dots. All 6 around oxygen, 7 around fluorine, and 8 around neon. So the tool here really is just looking at the periodic table to find the number of valence electrons by knowing that the group number represents the valence electrons, and those are the number of dots placed around the elemental symbol. When you find carbon, you can see that it's found in group 4A. So carbon will place 1 dot around each side of the elemental symbol. Here's oxygen, who resides in group 6A. So oxygen requires 6 dots around its elemental symbol. Fluorine lives in group 7A. So of course it's going to require 7 valence electrons. It does not matter which side is left with the lone pair. Here's hydrogen in group 1A, so it has 1 valence electron. Here's bromine in group 7A, so bromine will have a very similar dot structure as compared to fluorine, who's in the same column on the periodic table. Sulfur in group 6A. Sulfur also has 6 valence electrons, very similar to oxygen's dot structure. Chlorine, part of the halogen family, also with 7 valence electrons. And iodine, also in group 7A, so we would see 7 valence electrons. And if you find that pattern, the Lewis dot structures that would exhibit similar properties are those that lie in the same family. All with 7 valence electron, all are able to form 1 bond to fill its octet. These, oxygen and sulfur, would have similar physical properties because they lie in the same family as group 6A. So the same family, same column on the periodic table gives it the similar bonding properties. Let's review just some steps about drawing simple Lewis dot structures. And again, drawing simple dot structures, the idea is to obey the octet and to check formal charge. So we want to sum all valence electrons in the compound. What that means, for instance, is if we have a compound such as methane, CH4. Carbon lives in group 4, so it's going to contribute 4 valence electrons. Hydrogen lives in group 1, but there's 4 of them all together, so the hydrogens contribute a total of 4, meaning we have 8 electrons available for drawing a structure of CH4. The second rule says select the central atom, and I'll let you know that the least electronegative is always selected as the central atom, but never pick hydrogen. Electronegative. And what you want to say is who is the farthest from fluorine? Because fluorine is the most electronegative, we want the least in the center, but never pick hydrogen. So here our example would be carbon. It will be the central atom. Attach all other atoms back to the central atom using single bonds. That means all 4 of those hydrogens get attached back to the central atom. Remember that a shared pair is in this line, so we used 8. There's no more dots left. If there were more dots to add, we would fill the octet of the outer atoms and then place any remaining electrons on the central atom. And if we run out, we expand the octet or consider multiple bonds. So let's try a few and just kind of bring these back. CH2O, remembering how to draw Lewis dot structures for simple compounds. Well, carbon lives in group 4A, so it is going to contribute 4 electrons to this structure. Hydrogen lives in one, and there's 2 of them there, so it's going to contribute a total of 2 electrons from both hydrogens. And oxygen lives in group 6A, so it will contribute 6 valence electrons. So we have 4 plus 2 is 6, plus 6 more, we have 12 dots, 12 electrons. No more, no less, to place as we build this structure. Next thing we want to do is to select the central atom. And remember, it's always the least electronegative. Never pick hydrogen. So between carbon and oxygen, who's the farthest away from fluorine? Well, that's the carbon. Carbon is the least electronegative element. So it gets placed in the center. The next thing we do is attach all the atoms back to the central atom. That means with an oxygen to a single bond, a hydrogen with a single bond, and the second hydrogen with a single bond. And we've used 1, 2, 3, 4, 5, 6 electrons to do that, meaning that we have 6 electrons left. We're then told to place all the dots around the central atom, around the outside atoms to complete their octet. So we would find all 6 electrons being placed around the oxygen to complete its octet. That leaves us no dots left. However, carbon is electron deficient. In other words, at this point in time, we know we can't be done yet because carbon only has 3 bonds, and we've clearly learned that carbon requires 4 bonds. When we run out of electrons and the central atom does not have an octet, we know that we need a multiple bond. That multiple bond cannot come from hydrogen because clearly we understand hydrogen can only form 1 bond. So the multiple bond has to come from an oxygen. And what will happen is we're just going to take 2 electrons from the oxygen and bring them between the carbon and oxygen to form a double bond. So if I redraw, just cleaning that up a little, we have a C double bond O. Now we have 2 sets of electrons left in each of the hydrogen coming off of the carbon. We've obeyed the octet rule for each of these, knowing that hydrogen only needs 2 to be a noble gas like helium. So here, this is our correct Lewis dot structure for formaldehyde, CH2O. You have plenty of these on your homework to practice. We can certainly do a few more. C2H6, for example. Well, notice that the carbons are going to attach together. So carbon lives in group 4, and there's 2 of them in this structure, so it's going to contribute 8 electrons. Hydrogen lives in group 1, and there's 6 of them in this structure, so that means we have 6 dots to work with for a total of 14. When I connect the 2 carbons together, I've used 2 electrons. Now remember, we can attach hydrogens back to complete the 4 valence electron, the 4 bonds that carbon requires. And when we do so, those 6 hydrogens give each carbon the 4 bonds it requires. And in doing so, we used up 2, 4, 6, 8, 10, 12 electrons. We're all done. We've made a structure which each carbon has the required 4 bonds. What if we have 2 carbons and only 4 hydrogens? So we know the carbons will bond together. We have 8 electrons coming from the 2 carbons. Maybe I shouldn't take that shortcut. Carbon lives in group 4. There's 2 of them, so I note that there's 8 electrons coming from carbon. But this time we only have 4 hydrogens. So that means we have 12 dots, 12 electrons instead of 14 as above. So right now I've connected C to C, and that used up 2 of those, remaining of 10. So I have 1, 2, 3, 4, 5, 6 hydrogens. That would have given us the structure above, but I only had 4 hydrogens to work with. So I'm going to erase 2 of those and only allow myself to hook to each of those carbons 2 hydrogens. And in doing so, I use 2, 4, 6, 8 electrons, meaning I have 2 left. The 2 electrons need to be placed to complete the octet of each carbon, meaning that 4 bonds for each carbon can be achieved by a double bond in the structure. This simple molecule above is called ethane, all single bonds. This simple molecule is called ethene. It has a double bond. And can you make a prediction? C2H2? By the time we're done connecting C2H2, we will need a triple bond in that compound to satisfy the octet of each carbon. Molecules with a triple bond are known as alkyne, I-N-E. So this molecule is known as ethyne. Here we have a CH3OH. I know that the C and the O are going to bond together. Use the hydrogens to complete the valence requirements. Remembering that oxygen will have 2 sets of bonds. Or 2 sets of dots. Carbon, who lives in group 4. Hydrogen lives in group 1, but there's 4 of them all together in the structure. And oxygen, who lives in group 6. That means we had 14 electrons by the time we're done bonding. Each one of these shows a 1, 2, 3, 4, 5, 6. Here's 7, 8, 9, 10, and then completing here, 11, 12, 13, 14 dots. In HCN, H, we know, contributes 1, carbon contributes 4, and N will contribute 5. It lives in group 5A. So that gives us a total of 10 electrons. Carbon is the least electronegative element. Never put hydrogen in the center. We're going to hook back the carbon and the nitrogen, and that used up 4, giving us 6 remaining electrons. Complete the octet on the outside electrons first. That used up 6. There's none left. But here we can see that carbon is electron deficient. It's not done yet. It only has 2 bonds and it requires 4 bonds. So what we'll need to do here is consider a multiple bond where we slide in 2 sets of electrons. And so our resulting structure ends up with HC, triple bond N, and a lone set on the nitrogen. Is it coming back to you? I hope so. We often use formal charges in deciding the best structure for a compound. Formal charges was practiced in Gen Chem 1. Let's review that. A formal charge is associated with any atom that does not exhibit the appropriate number of valence electrons. And when it is present, a formal charge must be shown on the Lewis dot structure. So to be correct, we have to include the formal charge. Formal charge calculated takes the number of valence electrons that are assigned to that atom from the periodic table. And remember, you find that just by where it lives on the periodic table as its group number. and you subtract the assigned electrons to that element in the compound, all right? So group number minus assigned electrons. Let's kind of review what I mean by assigned electrons. All lone pairs and half of the bonded pairs are assigned to an atom in a structure. So let's take, for example, a compound with the central atom carbon. Let me draw it bigger. Here's the central atom carbon leading up to an oxygen that has 3 sets of pairs. And then these carbons are leading out to hydrogen. Do you find any formal charge? Well, one of the tricks I like to use is to take a circle and encompass each atom, bisecting every bond. And when you do so, inside of that circle, you will find all of the assigned electrons. Everything encircled is now assigned to that particular atom. Focus your attention on the oxygen. Oxygen lives in group 6A, so it has 6 valence electrons. How many circles, or how many electrons inside the circle? Well, I have 1, 2, 3, 4, 5, 6, and half of that bonded pair. So there are 7 assigned electrons, giving it a formal charge of -1. And notice how they're showing that as part of the actual dot structure in that answer. The formal charge of negative is placed right on the oxygen's elemental symbol in this compound. And it happens to be the only atom with a formal charge. Take a look at the carbon in the center. Carbon lives in group 4A, so it has 4 valence electrons. There are 1, 2, 3, 4 assigned electrons. Remember, each half of a bonded pair, meaning it has a 0 formal charge. Each of the hydrogens have 1 assigned electron, 1 electron inside of its circle. Hydrogen lives in group 1A, so it has 1 valence electron minus the 1 that's assigned, giving it a value of 0. So the one and only one atom with a formal charge in that example structure is the oxygen, and it was determined to be a -1. We can try a couple more from your homework. This one's asking, what's the formal charge? See how I'm abbreviating formal charge on the nitrogen. So as you draw that structure, draw a circle around the element that bisects each bond, because that's the way that we can assign 1/2 of a bonded pair to each element, so that the other electron then gets assigned for each of the hydrogens. So here we have N in the circle. Nitrogen lives in group 5A. It has 5 valence electrons. The number of assigned electrons are those that are encompassed inside that circle, which is 4. So nitrogen has a +1 formal charge and would need to be shown in the structure written as a +1 next to the elemental symbol for N. How about another? Find any formal charges in these examples. So I'm doing some homework problems. The first one, AlH4. I'm going to draw a circle around the aluminum, and inside that circle we can see that aluminum has 4 assigned electrons. Aluminum lives in group 3, so it has 3 valence electrons. But there are 4 electrons in the structure that it's assigned, so its formal charge is a -1. Let's find the oxygen in the second example. Draw a circle around its structure, and we have 1, 2, 3, 4, 5 assigned electrons. Oxygen lives in group 6A, so 6 valence electrons are what it would like to have. but right now it's assigned 5, giving it a +1 formal charge. And here I can see that nitrogen, who lives in group 5A, so 5 valence electrons, and inside this circle there's 1, 2, 3, 4, 5, 6 dots, 6 assigned electrons, making it have a -1 formal charge. Going the opposite way, I wanted to try some examples like this as well. Draw the structures and make sure that you can place the formal charge where it belongs. So let's model that with letter A, BH4 -1. Boron lives in group 3A, so it will contribute 3 electrons. Hydrogen lives in group 1, but there's 4 of them, so that's 4 total electrons. And the -1 charge means you have 1 additional electron. Adding electrons makes the species negative. So the total number of dots here is 3 plus 4 is 7, plus 1 more is 8 dots. Pick the least electronegative element, and that would be boron. Never pick hydrogens. Attach back all single bonds to that central atom. That used up 2, 4, 6, 8 electrons. So we're out of electrons. And notice that boron, who lives in group 3A, therefore has 3 valence electrons, has 4 electrons assigned to it, and that's where you see the -1 as the formal charge now on the boron. Let's try another, make it easier. NH2 negative. Nitrogen lives in group 5A, so it will contribute 5 dots to this structure. Hydrogen lives in group 1A, so it will contribute 1, but there's 2 of them, so that's a total of 2. And then the -1 charge means we get an extra electron. So 5, 6, 7, 8 electrons again here. We'll place the nitrogen and connect back both of the hydrogens, and that used up 4 dots to do so, leaving us 4 to place on the central atom. Notice that hydrogen does not get any dots. It only has 1 bond and it's done. So now nitrogen, who lives in group 5A, has 1, 2, 3, 4, 5, 6 electrons assigned to it, making its charge a -1. And the last one, C2H5 with a +1. Of course, we get the carbons connected together. We use the hydrogens to complete the valence shell, but notice that we're left 1 hydrogen short, 1 deficient, to create the octet on that second carbon. So therefore, that's why we see the +1 assigned to it as a formal charge. It is electron deficient, knowing that carbon would like to have 4 bonds, but that particular carbon only has 3, making it a plus overall. Carbon lives in group 4A. It has just 3 assigned electrons next to it, making its formal charge a +1. Let's pause the video here and come back when you're ready for polar covalent bonds.